charge in the middle of it, positive Q, and I think we already looked at R is less than R1. Yes.
Can you close the parentheses? It's going to drive me nuts.
Thanks.
Thank you.
So now let's look at between R1 and R2. So that's in this region here. I think I'm going to go a little bit faster here. What's the E field in that region?
Zero.
Zero. Okay. And so therefore, what's the change in potential in that region? Zero. Does that mean the potential is zero?
No.
No. Okay, now I'm going to do R is greater than R2, so it's out here now. Notice it's enclosing negative Q and positive Q. What's the E field going to be? Zero. Can I go quick like that? Yes. Okay. So what will the change in potential be? Zero. What will the potential be? Will the potential be some number? Well, think of it this way. I know that the potential, let's say right here, I'll call that C, and I'll put D way up here at infinity. So the potential at C minus the potential at D has to be equal to zero. What's the potential at D?
Zero.
Zero. By definition, at infinity, potential is zero. So what's the potential at C then?
Zero.
Zero.
I have a question. How is the E field for the middle part zero? I know that there's nothing enclosed inside the conductor, but don't you have that middle?
Well, if I were to draw my Gaussian inside the conductor here, remember that since there's a positive here, it's going to induce a charge in the conductor. What charge will it induce on here?
Equal and opposite.
Yeah, negative charge. So what's the total charge enclosed in?
Zero.
Zero. And maybe we should talk about a little bit what will really be on the outer surface here.
Positive.
Let's see, this is going to be negative Q, and so therefore this one would have to be nothing.
Zero. But if it was neutral.
Yeah, then it would have, but it would have to be nothing, right? Because it's inducing all that negative charge onto the inside surface. So I need to go back then. So what's the potential at C here? Right here, it's zero. So if we're looking at the two curves here real quick, E versus R, and we have R1, and we have R2. Inside here, do you remember what that was? That was the inverse square. So something like that, inverse square. And then from R1, R2, that's zero. And then beyond R2, it's zero. So now let's look at the potential. Let's start with infinity and work our way in. So infinity is what? Zero. And at R2 it's going to be zero. Now R1 it's going to be zero, right? So I needed to go back up here because if I know there's no change in potential in here, and I know this is zero, what does this have to be? It has to be zero as well. And then what kind of relationship would I have in this region here?
1 over R.
1 over R, it's an inverse. So this is 1 over R squared. This is 1 over R. Probably something like this. 1 over R. Any questions?
Would never have negative voltage and that negative charge?
We would not. Because when you're looking at the E field here, total charge enclosed would be zero. Any other questions? Okay, did you have to try that one at your own self at home? How did you do it?
I didn't know what to do for the last part. So I didn't know if it was really negative Q or was it just type
Okay.
positive.
But you got the E field stuff?
Yeah.
Explain why R squared and R1 R squared.
So here or here?
I think secondly.
Okay.
Why can't
Hey, wait a second, I'm going to pick two other points. How about pick A and B? that means right here, the potential at A has to be equal to the potential at B. Some non-zero number. Yeah, why can't they be some non-zero number? Let's take the limit as B goes to the surface. And I already took the limit as C went to the surface. What must be true about the potential of B compared to the potential of C? Same. So if this is all 0, then this has got to be 0, and now this has got to be 0. Okay. All right, any other questions? Okay, let's go on to the next page. Okay, so I have this cylinder of charge. It's kind of a shell. And so I'm looking at R is less than big R. So this is going to, the E field, if I make my Gaussian, oh, R less than, okay, so it's going to be in here. So here's my Gaussian. This should be easy then, right? How much charge did it enclose?
0.
So the E field is 0. Okay. So what will the change in potential be? 0. Does that mean that the potential is also 0?
No.
Not necessarily, right? In order to figure out the potential is 0, what do I have to do? I got to figure out the potential here at the surface, right? Okay. So now let's go ahead and look at that part. R is greater than big R. So I'm looking at a Gaussian out here. So if I look at the E field through that surface, can we see that it's constant because of the geometry? It's constant. So I'm going to factor that out. From the E integral dA equals Q enclosed over epsilon naught. Non-calculus people, if I sum up, anti-differentiate dA, this dummy variable, what's that become? Just A. So that's EA equals Q enclosed. And further, let's say that this, and I don't know if I told you this yesterday, let's say this has a charge per unit area. So in other words, if I took the charge per unit area, that gives me sigma. So Q then is going to be sigma times A.
A's canceled.
A is canceled. So I have E is equal to sigma over epsilon naught.
What would we plug in for A if we actually?
I feel like I forgot this.
Wait, the A's aren't don't cancel because they're two different.
Yeah.
Oh, right.
Because one is with big R, one's
You're right,
with
you're right.
little R.
Thank you, thank you.
Nice job, boy.
That's what happens when I don't look at my notes. Okay, so I have to figure out the area of the Gaussian. So let's see, this is going to be E, still A. You're right, it is different. I'm going to say A1 equals, or A of G, Gaussian. And this is going to be sigma times the area of the actual cylinder. Thank you. Okay, so then the Gaussian is going to be, what is the area of the cylinder? It's just this part of the cylinder. Pi little r times L equals sigma. The area of the cylinder is going to be 2 pi big R times L. Thank you. Epsilon naught. Now I can cancel this. I can cancel the 2 pi. I can cancel the L. And I get E equals sigma R over epsilon naught 1 over R. Is that what you guys got? Okay. So now I'm going to integrate this. Let's say we integrate it from B to A. So the voltage of A minus the voltage of B equals negative from B to A, sigma R over epsilon naught times dr. Wait a second, I dr says to only look at which variable? Little r. So this is going to be negative sigma r over epsilon naught from b to a of 1 over r dr. I can get rid of the negative sign by reversing the limits of integration. Is that okay? Okay. So, and then if I anti-differentiate 1 over r, this is one of those exceptions to the power rule thing. This is natural log. Okay. So this is going to be equal to sigma r over epsilon naught times the natural log of r. And I'm evaluating from a to b. This is equal to sigma r over epsilon naught, natural log of b minus natural log of a. I can use the property of logs, and if I subtract logs, that's the same thing as, yep. So I'm going to replace this with, I'm going to do a little bit of erasing here. I'm going to replace this with natural log of b divided by a. B divided by a, is that going to be a, is that going to be a number less than 1 or more than 1? That's going to be more, right? Because b is further away than a. Okay? Because the reason I'm pointing that out, what's the natural log of 1? It's 0, right? So I'm not going to get, I'm going to get a non-zero number here. Also, here's the problem. This is why I put it in gray. If you said that b was infinity, what's the natural log of infinity over r? Yeah, it's kind of undefined, right? So there's actually more that we'd have to do here, and that's not on your AP test, okay? Yes?
I'm just wondering, how do you know where to put like A and B for potential?
It doesn't really matter. I could have called this one C and D or whatever, and I could have went from, instead of going from B to A, I could have went from A to B. It would still work out okay.
So I can put like this out the voltage of A minus voltage of B.
I just, well, no, I just put 2 points here. I could put X and a Y if I want to.
Does it matter how you put it under this?
Well, this does matter. I can't write this and have this. This is not right. That's not right. Because what I want to know is what's the voltage of A minus the voltage of B? Well, when I sum this up, I'm going to be plugging in B first. And so this would be B minus A. So that's not okay. It would have to be like this. Now, if I wanted to, I could go B, voltage of B minus voltage of A. There's nothing wrong with that. And so in this case, then I would have B here and A here.
And then it would be negative.
It's still, this would still be there. Everything's the same. My answer at the very end might be, in fact, it would be the exact opposite of what I have here. It'd be negative. But it's totally appropriate. Nothing wrong with it. Any other questions? Okay, then I'm going to go on. Let's see, what do I do? Oh, in the first part, we found the potential in here. There was no change of potential, but we don't really, we can't really say what the potential here is unless we figured out what the potential is. So you see where there's some problems here. That's why I have all this in gray over here, because you have natural logs.
Are we really not doing this?
You really won't. On your AP test, I've looked through all this stuff. You will not see finding the potential. You will find the E field.
You seen our AP test?
I've looked at past ones, yes. You won't find the potential for a cylinder. Or even for a line charge, because if you remember, that was 1 over R as well. And so when you integrate, you're going to get natural log.
Are you going to have us do this for the test then?
Maybe. For instance, the very last one, where you have a nested cylinder, while it's true I can't figure out what the potential is with respect to 0, or with respect to infinity, I can figure out what the potential is at one cylinder compared to the other cylinder.
So like in between?
Yeah.
Okay.
And that's where hopefully we'll get to here in a second. It's still kind of good practice to look at it, I think. Okay, look at the next cylinder. I'm going to use the same picture and say now it's a now it's an insulator. Okay, so for this insulator, we're looking at R is less than big R. And I think for an insulator, I could say it has a charge at Q, but I think it would make sense that it has a charge density rho, which would be a charge Q per unit volume.
Does it matter if you use sigma or rho or?
No, it doesn't. Okay, so for this, it's going to be inside. It's going to be, if I make it Gaussian inside here, hopefully you can see the E field's constant through that. And so it's going to be E times the area of the Gaussian equals the density times the volume of the Gaussian over epsilon naught. It's not going to be the volume of the whole cylinder, right? Because we're looking at the Gaussian inside there. Now, if you didn't have the density, if you just wanted to have it in terms of Q, then you're going to have to multiply by a ratio of the volumes.
So it would be the volume Gaussian over the volume of the entire thing.
Right.
If you didn't have.
Yeah, if I didn't know the density. But we all know that if you take density times volume, that gives me the charge enclosed. So can you see that if you know the density, it actually makes it a little bit easier. You don't have to do ratios of the volumes or anything like that. Okay, so my area of my Gaussian is going to be equal to 2 pi r times L. Density times volume of Gaussian is going to be pi r squared times L over epsilon naught. The pi's cancel, the L's cancel, the R cancels the square, and I have the E field is equal to the density times R over 2 epsilon naught. You know what? I think I want to do this because I'm getting a lot of blank stares here. I have a feeling you guys did it a different way. I'm going to keep this here so you can look at it. I'm going to erase this part though right here. Let's say I don't know the density is rho. Let's just say charge on the whole thing is Q. Okay, so in this case it's going to be E times. Is that how you guys did it?
Yeah, I
just
just erased
erased it.
all of it and wrote the row away.
Well, wait a second. I'm going to show you both ways, and I want you to see that the answers are basically the same thing. Okay? So I'm going to use this over here. But I just want you to be able to say, oh yeah, I got the right answer doing it that way. Okay, so that equals Q enclosed is going to be the ratio of the volume. It's going to be the ratio, the volume of the Gaussian, which is pi little r squared L over pi big R squared L over epsilon naught. The area of the Gaussian is going to be pi r L. The pi's over here cancel, the L's cancel, and the R cancels the square. So I have E field is equal to Q times little r over 2 pi big R squared epsilon naught.
Yes.
No.
No, thank you. So can you see that both of these are a factor of what? Compared to R. Can you see it's related to R? It's directly related. So they're the same idea. It's the same thing. It's just that this is charge per unit volume, and over here it's just simply charge. If I figured out the units, I could get the exact same.
Is the Q there, or rho is Q over pi big O squared L.
It's the same thing.
Which one are we going to do?
I thought I'd do this one.
Okay.
I just wanted you to be able to see if you did it right. Okay, so now I'm going to, let's say I integrate it from B to A. So this is going to be potential A minus potential B is equal to negative from B to A of looking at this, notice all that stuff is constant except for the R there. So I'm going to put it like this, density over 2 epsilon naught times R dr. So that becomes density over 2 epsilon naught. When I integrate this R, it's going to become R to the what power? Squared. Notice I still will have that negative, so I'm going to reverse the limits of integration and get rid of the negative. So it's going to be B here, A here, R dr. So that becomes, when I integrate that again, what do I get? I get R squared over 2. Don't forget that. So this becomes density over 4 epsilon naught times R evaluated B squared minus R evaluated A squared.
Okay, why did we achieve that?
Okay, so let's play the anti-differentiation game for.
Oh, no, I got it. I got it.
So if A was, let's take A to the extreme. Let's have A be right at the center. What would A be then? All right. It'd be 0, right? So then I can figure out what the potential is at B compared to the center. So that would be a legitimate question. Notice there's no natural log, there's no infinity or anything. That would be legitimate, where I ask you, what is the potential at the surface compared to the center? And you would simply say density or charge density over 4 pi epsilon naught times the radius of the thing, R squared.
So you'd be more likely to give us one like this.
Something like
You
that.
can actually solve it.
I don't know something that I would give, but that would be something that the AP would give too. Now realize that's not the absolute potential, that's just a potential here compared to here. So that would be an exception. Okay, let's look at outside.
Are you gonna go with, yeah, obviously, that's it.
So R greater than R. So this is going to be E times the area of the Gaussian equals Q enclosed over epsilon naught. Let's stick with the idea of rho. Is that okay? So that means Q enclosed is going to be rho times the volume of the cylinder, which is 2 really pi big R squared L. The area of the Gaussian is 2 pi little r L. The pi's cancel, the L's cancel. And so I get the E field is equal to the density times R squared over 2 epsilon naught 1 over R. When I integrate this in a little bit, what am I going to end up getting in the end?
Natural log.
Natural log. Okay. So when I plug in the limits at the surface, let's say, and at infinity, will it make sense? No. Okay. Do you want me to go ahead and do it though? Can I go ahead and move on then? Okay, I'm going to go ahead and move on to the conductor next. So now it's conductor, and I draw a Gaussian inside. What's the E field going to be? 0. And now I integrate the E field. And so what will the change in potential be? 0. Does that mean the potential at the center is going to be 0? No. But we do know the potential at the center is going to be the same as
The other.
the potential at the surface.
Yeah.
Okay, then let's look at R is greater than big R. What do you guys want me to use for the charge? Do you want me to use Q? Do you want me to use sigma? Do you want me to use a line density? What do you want to use?
Q.
Q? Well, I thought that some students might use a line density. I don't think you would be appropriate. I really think it would be sigma, but I don't think there's anything wrong with saying the line density. It is, has a certain length. Q? Sounds like Q is what you want. Okay, so Q. Okay, so for greater than, and I have my Gaussian already there, so it's going to be E times 2 pi little r L is equal to Q over epsilon naught. That means E is equal to Q over 2 pi epsilon naught L times 1 over R. So how'd you do? Did you get it right? Okay. Now I'm going to integrate, let's say, from the surface, from infinity to the surface. So the potential at the surface compared to the potential at infinity. So surface, infinity. And all of this is constant except for the 1 over r is what we're looking at. I can reverse the limits of integration to get rid of the negative sign. And I can pull out the constant. And so it becomes Q over 2 pi epsilon naught L natural log. I'm going to be subtracting these two, so use the whatever it's called for logs, property of logs, and that would be at infinity over the surface. In other words, the potential at the surface is a lot more than it is at infinity. We knew that already. Since at infinity it's really what? Zero. So there's actually more you would have to do if you encountered this in college. You actually have to look, you have to integrate along the length of it. Basically the problem is we're looking at an infinite conductor here. Okay, well, infinite conductor, that's a lot of charge. So probably wouldn't make sense to have an infinite conductor. It has probably some non-infinite length, and you would integrate along the length of it. It becomes more complicated. It's not on your AC test. Definitely not on the BC test. Okay,
So the B exam.
right now I'm killing the B exam people because they're like, oh my God, we can move on. They don't have any of
We
that.
had arts.
And yet most of them have been in.
That's right.
Like optics.
Nope.
That's right.
Those two have, I haven't.
I thought you could go.
Okay, let's look at the next one.
Also, this is massively
What
jumping
are
my
you
grade, and it's not on the
doing?
AP test.
You didn't like drawing all these lines?
Yeah, but it's still part of your
Oh my god.
Wait, but Jack, what
Jack, that's
happened?
exactly how we felt though when we were.
He uses the distraction.
Okay, so the last one on this page, we're getting there. So now I want to figure out what the E field is when R is less than R1. So that E field is?
Zero.
Zero. Okay. No questions about that? Okay. So when I integrate this, what would the change of potential be? Zero. Does that mean the potential is zero? Okay. Okay, then looking at the next one. R is between R2 and R1. So this is going to be E times, do you want me to use Q?
You told us last time.
Yes, that's right. Q1 and Q2, that's right. Okay, so E times the area of the Gaussian, that's going to be 2 pi RL equals Q1 over epsilon naught. And so that means that E is equal to 1 over 2 pi L epsilon naught 1 over R. Let's take it to the most extremes. The extreme E field is going to be 0. So what will the change of potential be? Change of potential is 0. So let's say I have the extremes of at R2 compared to infinity. So what will the potential of R2 be then? That'll also be 0, right? Yep. So we have this answer right here. This is the potential at R1 compared to R2, but it's also the potential at R1 compared to infinity, right? So this is the absolute potential at R1. Think about the previous one where the E field's 0 inside here. What must be true about the potential inside here then? It's the same as that, right? So in other words, here's the graph. Okay, so E field in here is 0. And then in here, I believe it's an inverse relationship. Is that right? Yes. 1 over R. And then it goes back to 0. So now let's look at the potential. The potential out here at infinity is 0. And at R2 is 0. Is it 0 in here? No, it's not, right? In fact, what's the relationship? What kind of graph would I be drawing here? And I don't know how to draw that. Oh my God. It's not like this. It's the inverse of that. I think
it's like upside down.
yeah, I think and I probably actually need to connect it too. It kind of looks like inverse, I think. Yes, it's an upside down natural log.
So negative natural log?
Negative natural log, that's right. And then it gets up to this point here. Well, what is that point? That's really what I was aiming at. What is that point? What's the, it's that over there, isn't it? That right over there. Go ahead. Please don't make me write it. You understand what I'm pointing at? It's this. Okay, how will I?
Pretty far apart. I don't think I can't think.
Okay, then what about this part right here? What about this part right here? Is it 0? It's flat up here, right? Yeah. Yes.
Why is it a negative natural log?
Because the relationship between the potential, the change in potential, and the E field is related to the negative. Remember the slope of this, the negative of the slope of this gives you this.
Right.
So this right here, if the slope of this one has to give me, actually, negative slope of this one has to give me this. Well, the derivative of natural log is 1 over R. And so if I have negative natural log, so that's going to be negative 1 over R. But then I have that negative sign out front.
But did we kind of already get rid of it by switching the limits? Like no, we like switched the R.
Yeah, that was a mathematical thing that we did to help us find the answer. But this is still conceptual.
Okay.
That's still true. Okay, I think I can actually get through the rest, I think, maybe. Because they're all very similar. So how are you guys doing on this? Doing okay?
Yep.
Okay, the last one, or last page, I should say. Okay, I think it would make sense in this case where we have these charges here to call the charge area step Q because it's an infinite plane. I think it would make sense to say it has a charge per unit area, sigma. I'm going to draw a Gaussian in here. It could have any shape. It doesn't have to be, I'm getting ready to draw one that's a cylinder. It doesn't have to be a cylinder. It could have any shape. That's not really the important part. The important part is that it has a certain area and that E field is coming through that area. Just that way. It's not the other direction. And the area vector is that way too. So this is going to be E times A. The area of Gaussian is true. Over here, this is going to be sigma times A. And that is the same A this time. I didn't make a mistake this time. Over at 1 Because truthfully, that Gaussian could be infinitely large, just like the whole plate there. And so now the A's cancel, and I get E field is equal to sigma over epsilon naught, which is constant. That's right. So now I'm going to integrate this constant. In fact, I'm going to pull it out. Negative sigma over epsilon naught from, I'll say from the surface here to infinity. So from the surface to infinity. Oh, surface. And that's dr. So when I integrate this, what will I get here? That's going to give me r. So this is going to be, I can reverse the order of integration, right? Okay. And it gets rid of the positive or negative sign, so it's going to be sigma over epsilon naught times r. So in other words, what it's saying is the potential here at the surface is infinitely larger than it would be at infinite distance. That's still a fair question because usually they won't ask you at infinity. It'll ask you, compare the voltage here to the voltage here. Okay? And so all you would have to do is know what that distance is and you can compare the voltage.
So you have to still,
Shouldn't that end up being a negative? Because you have a small.
All right, I switched things here. So I switched it from R. I put infinity here and surface here, which would be 0. It doesn't be 0. And so if I plug in infinity here, what it says is the potential here compared to infinity is infinitely large. But usually they won't ask you to infinity. It'll say, okay, this point here is 10 centimeters away, which would be 0.1 meters away. What is the potential here compared to 0.1 meters away? And all I'd have to do is come over here and plug in sigma over epsilon naught times 0.1. And it'd give me the potential difference. The difference, exactly, the difference.
no, they said like from point 1 to point 2, then you have to go back.
Well, what I'd have to do is I'd have to plug in I plug in these numbers.
Yeah.
I plug in 0.2, figure out what it is, plug in 0.1, figure it out, subtract the 2. But really, it's going to be the same thing as just 0.1, isn't it? That's going to be the difference.
Yeah.
Why is that true? It's because the E field is constant. Okay, each one of these, the next one's going to be exactly the same thing, so I'm not going to repeat that one. The reason why it's the same is I have another plate up here, yes, true. But my Gaussian doesn't go through that. It still goes through this part down here. I get the exact same answer.
What if
If I made my Gaussian go through the entire thing, you can make a Gaussian go through the whole thing. What's the charge enclosed? 0. 0. In that case, it would be 0. But if I want to figure out just the potential in here, I'm going to draw a Gaussian like this. Okay, then the last one. This is an infinitely thin sheet. And this has changed just slightly because when I draw my Gaussian in here, again, any shape, it doesn't matter what shape of my Gaussian is. There's going to be an E field coming out this side, but there's also an E field coming out this side. And so when I do this, it's going to be E times 2A, because there's two areas it's coming out of. Equals sigma times A. And again, this Gaussian could be infinitely large, just like the sheet is. The A's cancel, and I have E is equal to sigma over, over 2 epsilon naught. So how would the answer over here change then? Yeah, it's just going to be 2 epsilon naught over down here at the bottom.
So why do you have 2A? Oh, because it comes out both sides.
Yeah, it's kind of, you have the E field coming out both sides because it's infinitely thin. It's just a sheet of charge, I should say. It's a sheet of charge. So I do have a question. When you compare this one with this last one, where it's over 2 epsilon naught, which one's going to have a greater change in potential? The capacitor is, right? Because this last one's going to be 1/2 of it. Okay, so that's the end of that. I'm hoping you're trying some of the internet homework because on Monday, we're going to start working on some of those recitation problems, and I'll also take any questions you might have about some of the internet stuff.